Hello everyone, I'm Silent Death, and welcome back to a Stationeers No Mining Challenge. Last episode, we worked on automatically emptying this little vending machine and sorting all the outputs. Between episodes, I've done a great deal of trading, including buying a couple of AIMEEs. So what we're going to do in this episode is finalize and finish our AIMEE setup that we have over here, going towards something more than individual AIMEEs and into more of an AIMEE swarm. But first, there are a few things that I did between episodes that we need to look at. A few little changes in what we did last episode. So for this part, I noticed that when I left and this shut off and then I came back, these little sorters and stuff were not getting turned on right away. So I tweaked this. Right here. I made this a whole separate function where we turn them on and off. And all this is basically the same. I also added these lines in each function. This is just mostly because I'm paranoid. I want to see the script that's actually working before I buy explosives and stuff, exploding canisters. So just having it there for me to see just makes me feel a whole lot better. So these have been added to every single function down through here. But for this, we're doing basically the same thing we did before, except for right here. If we're turning the riders and meters off, we just return. Otherwise, we yield and jump to main. This will be where it gets shut off. This ensures that this gets rerun at the start of when it gets turned back on. That's all I wanted to do. I could change it up to have these first and then a yield and then this stuff below it, but I didn't want to do it that way. Now, I've also made some changes into our vacuum gas canister recycling area. Now, here in this room, I expanded the number of active vents to 3, 1 in each cell, or 1 in each grid, whatever you want to call it. And I also removed the delay between checking the pressure that I had built in, checking the slots and checking the pressure. I had a bit of delay, but I removed that for I was still taking a little bit of overpressure damage, so I just want to get rid of this. They seem to work fairly well. It pumps the room out quite fast now. Also, I remembered something, or possibly remembered something. I think someone on Discord said that these active vents can spark an atmosphere and ignite it. I'm also not sure if this or this can spark an atmosphere and ignite it, but I wasn't really willing to risk it, so we've added volatiles and fuel canisters now go into the furnace. And that meant we had to add a gas pump to the furnace as well. And that's kind of, snaking around and made this little liquid pump pretty awkwardly placed. It's kind of half in a room. It doesn't look good. It doesn't at all. But it works. So that's that part. And we have, quite a lot of gas in there already, so I bought a fair amount of gas for this. This got simplified a whole bunch because we deleted the count stuff, and then we just added a gas pump setting to the right after the pump, and then we used hash batch commands for the vents, and then we added another setting for the gas pump as well. But that was fairly simple. Just, this is safe. I could try to test to see if this stuff sparks the atmosphere, but I could never be 100% sure if I just was getting lucky and it not igniting or if it didn't actually ignite stuff. So I just went ahead and had all the gas go inside of the furnace. So that's all we've done between episodes. Now this episode is going to be a little bit different. It's going to be a little bit math heavy. Not hard math, but still it's going to be math. Because what we're going to do is, like we had in the furnace area, we're going to have a manager script that's going to control all of the IC chips, or kind of talk to all the IC chips that are inside of everything. So the IC chips they'll have these IC chips that control their little AIMEE, and then we'll have a manager IC chip. It's going to be somewhere like right in here. And of course, with my favorite little hidey thing there, we'll have something here that's going to be a kind of a master controller. And this master controller is going to control the waypoint, not the waypoint, but the mining location. Let's pull out this. It would probably be easier if we look at it while talking about the code. So right now, we have our mine X, Y, and Z. And what we're going to do is change this to, instead of be constants, they're going to be provided by a master control chip over here. And whenever this little guy goes to the mine X, Y, and Z, and then it will look at minables in vicinity. And when that number is 0, or maybe when it's just very low, it will write to the X, Y, and Z, and it'll write 0 to it. And then this chip over here will read that 0 and give it the next coordinates. And what we're going to do is we're going to create a spiral that's centered on our base. And it's going to assign a coordinate based on a few things. So first, let's switch over to MathCAD. The equation for a spiral is basically the polar coordinates equivalent of mx plus b. It is a plus b times theta. Radius of theta equals a plus b times theta. And a is the distance from the origin. So if we set a to 0, and just do our theta equals b times theta, we get this little spiral here. And that is the basic spiral. This is Archimedes spiral, I think it's what it's called. You can have things where the distance isn't constant, but we want the distance between the spirals to be constant, because this is the distance that the AIMEE checks when it's looking for ore and stuff. Now to get a little bit more mathy. We have the spiral. Okay, now we have the spiral here. We have this spiral, and we know that this distance is good. The distance between these is good. What we don't know is the distance between the lines. The individual points on the lines, we want those to be also the same distance as these. The search distance, basically. So the distance between 2 points in polar coordinates is this formula right here. The distance equals blah, blah, blah. And if we set a to 0, substitute in b times theta for theta 1 and theta 2, we can simplify this equation. So we set this to b, and we do that substitution. We get this, which solves equations in terms of thetas, so we don't have as much calculation to worry about. Then, if we rewrite a, in this case, a is going to be the radius of our base. So instead of having a that we have to substitute in, we just won't start theta at 0. We will say that this is how many revolutions we need to add to theta. So it's a divided by b times 2 pi. So that's the number of revolutions we have to add to theta so that b is a distance away from the origin. And then we cannot solve this equation in terms of theta. Or if we can, this program can't do it, and my math is just not that good. We do. I think we can't work. Okay, so that doesn't work for us. So what we need to do is to solve it numerically. That means basically we calculate it and try a guess value, stick it in the equation, and keep calculating it until we get into an acceptable range. In this case, the acceptable range is going to be this equation equals 1 to 1 plus 1 over b, which is equivalent to 1 coordinate. So it's going to be between b and b plus 1 in terms of b is going to be in coordinates, I think. I'm not sure about that. I may need to adjust that. I'll have to check. But there's also an equation to convert from polar coordinates to Cartesian coordinates, and that's like sine of theta and something like that. It's sine and cosine and stuff. That should be fairly easy. It's like r cosine theta and r sine theta. Okay, so that is the basic equations we're going to be using for the manager script. The other difficulty we're going to have is let's switch back to Stationeers. Okay, the other difficulty we're going to have is these waypoints. We do not know where it's going to be in terms of our base. Since it's going to be somewhere on the spiral, it can be at any point. That means we're going to need 4 different waypoints. Well, 5 different waypoints. 1 at each corner. And then 1 right before it enters. So we'll need an additional 4 waypoints. Then it needs to somehow figure out which waypoint it needs to go to. And we need to fit that all in like this many lines. That's not good. That is not good. We may have to move some of this stuff onto the chip that's inside the AIMEE robot. I'm not sure about that. We'll need to figure something out there. That's going to be one difficulty. The spiral program, I think it's going to be fairly straightforward. I think we can fit that fairly easily. I spent a while simplifying those equations to make them easier to program. Then, okay, so how we're going to do the coordinate thing, the waypoints, what we'll do is we'll have, say, a waypoint that is, right now we have a max z. That's, I think, negative 20. Yeah, it's like, if it goes anything below this, then it turns around and goes back. But what we'll have is a group of lines that, connect into a square around our base. And if it's anywhere in this direction, so if it's z is less than whatever, then it goes to the 1 coordinate. And if z is greater than this, then it's going to need to check. Let's see, the case that z is between next case will be it checks if z is going to be less than this. Yeah, it's less than this. So z is going to be less than this number that's going to be this side. It will check to see what the X is. So if X is going to be this direction, it will pick a coordinate that's going to be that corner over there. If Z is over there, if Z is right here and X is over there, it'll pick that corner. Then if Z is in this area, but X is over there, it'll pick the corner over there. Then comes the case when it's on this side of the base. So in this case, what we'll do is we will read the coordinates of this, and we will check the two corners there, and whichever one is closest to, that is the one it's going to go to. So we'll use the distance between 2 points formula, calculate that. Just using the X and Z coordinate. We don't really care about the Y. There's no reason to add that complexity. And additionally, I may want to add one more thing. Given that we're using, not path to target, but the other one, the move to target one, we probably want to have some way to check to see if it gets stuck. And we'll do that by maybe checking the Y coordinate and adding some kind of alert for ourselves. If the Y is, below whatever, below like -1 or something. I think -1's probably pretty good. Maybe -2. I think -1's a good enough sake to check. So what we need to do first is pick the, boundary settings for our base, and we'll probably have to tweak these a little bit. And then we need to pick some waypoints that are outside of those, and we need to try to program some stuff. So what we're going to do is we're going to be using the stack to program these, I think. I think the stack makes the most sense, instead of just having to refer to them the other way. Okay, so I need to do some typing, and I will be back. Okay, so the initial stage of organization is done. We've rearranged these guys so that we'll have 3 LEDs on each chip. We'll have charge, mode, and the minables in vicinity, or whatever it was. Minables in vicinity, yeah. So those will be the 3 outputs that we keep up with probably something in the housing will be the RA or whatever. Each of those are set, and we have each of our AIMEEs inside their little cubby holes. Then over here, we're going to have the red memory is going to be theta. The theta that we're, looking for, because we don't want that to be reset if we take the chip out. We want to keep it to memorize it so that it doesn't reset the whole clockwise rotation AIMEE thing. Then we have 2 memories for each AIMEE. So that'll be the X and Z coordinates of the mine location that we're going to have. And other than that, I guess it's time to actually do the programming part. Okay, so I've been working on this for 6 whole days. This did not want to come together. First, let's go over what we've built. I don't remember exactly where we left off, but I just went and checked, so we kind of know where we're at. We have the AIMEE on screw 1. Then we have the LED for the charge, the LED for the mode, and the LED for the minables. Then we have the memory for X and the memory for Z. And all this is all color-coded, so we know where everything is. Nice and neat like that. And these are also named so that they're in alphabetical order, starting with this one. And this one is named the theta logic memory, so it's going to be the last one in this whole list. Now then, we have the chip that goes inside the AIMEE, which I've moved outside the AIMEE and put in this little temporary circuit thing for debugging purposes because, you can't really debug a chip when it's inside the machine. Alright, so we've got those, and we've got spray paint and all that stuff, and we got this done. So this one has data logic memory, and then the logic transmitters for the 4 AIMEEs. We can use the index command and just have an infinite number of AIMEEs, but I decided to do it this way for now. Out here, we've got our little swarm of AIMEEs waiting for orders. So let's go look at the code. I am going to switch over to the simulator now, so shield your eyes from the bright light. Okay, so we have this. This is the chip that goes inside the AIMEE. This is the first one we're going to look at. This chip has exactly one job, and that is to pathfind back and forth to our little hangar area. So we have the alias of the device space is dbot. We're just using the same name for all the bots for all the chips so that it's, easier for us to copy and paste things. Like I said, I've been working on this for 6 days and things have been moved around a whole bunch. We have this 2 coordinates. So these 2 coordinates are the coordinates that are actually inside the hangar. Then we have these 2 coordinates, which you can see the X lines up, and it's just a different Z. This is the original waypoint that we had in the last script. The one that's kind of just outside the hangar. So it would be the coordinates that are right here for this AIMEE here, and then 14.5 is actually inside the ring. This allows it to line up from this coming in from the sides. Now we have these 4 numbers, which are they define the rectangle that is our base. It's the boundary box for our base. Our AIMEE will stay outside of these numbers while it is mining. It will only go inside them when it is pathfinding back to the hangar area. Then we have 4 waypoints on each corner of our base. So southeast, northeast, southwest, and northwest corners. And these are just, I walked out there with the little GPS chip and picked the spots and, decided they look good. And pick those numbers, which, they match up with the numbers up here. Then this little select area has been cut down from how we had it in the previous script. We're only looking at unload and storage full. If these little areas bother you when you're using the simulator, you can of course just use the regular numbers, but I like using it this way so that I don't have to go back and look up the numbers. Or I could just look at it doing like this and use the numbers. It doesn't matter, whichever way works for you. We have also a cut down read data function because we're only checking these few things. We're only checking the mode, the position X, position Z, and the charge ratio. Then full, we have move to shelter. And move to shelter is saves to RA, and then it goes to path to home. Path to home is complicated. This was one of the big things that took a lot of time. So the first thing we're doing is we're saving the RA again. Then we're saving the stack pointer. So this is the stack pointer that's at the end of our waypoint list here. Then we are moving our waypoint stack pointer to 100. We're going to build our path starting at the stack pointer of 100. That's kind of just our number that I picked out of nowhere. Then we're starting the stack pointer at the default waypoint, which is, a waypoint that always gets put in. because that's always going to be there. It always has to go to right before the hanger and then go inside. So we're adding that. Add waypoint is down here. It peaks and gets X from the waypoint. Then it adds one to the stack pointer and gets the Z. And then it moves the stack pointer to the waypoint stack and pushes those two numbers onto the stack. So basically, it comes up here and reads the two numbers. Then it jumps back to where our waypoint path list is going to be, and it sticks those numbers onto that area of the stack. Let's see, where were we? And here we're having a whole bunch of relative jumps with numbers and doing things, and this is going to be a little bit complicated to explain. But we're looking at our position Z and max Z. So if we're already on the side where the hangers are, we only need to worry about that one waypoint, and we can skip everything else and just jump down to here and continue on. Then otherwise, we need to check our X coordinate. If we're on the south side, then we put the southeast waypoint. If we're on the north side, we put the northeast waypoint. And yeah, that's right. Then we have this part over here, which is when we're on the far side of the base. That means we have to add 2 waypoints. And this is a little bit complicated because we might end up with 2 of these type of waypoints, but it shouldn't make a difference because it'll do it and then it'll get deleted. So, we might have an extra waypoint, but it doesn't matter. We have plenty of space on the stack. And trying to do this would, we're running low on lines of everything. So right here is where it is loading or moving the stack pointer to the waypoint that it needs. And then it's just adding that waypoint to the path. So we do that for the 2 X's and then the far side right here. So first we need to see which one of these 2 we need to add. So whether we need to add the southeast or northeast guy, and we're just using a select command. So select is if R equals 0, I think. I think that's right. Anyway, if R equals 1, it is, if you have R equals 1, if R equals true, in other words, so if this command is true, or if this statement is true, then we do the southeast waypoint. If it's false, we do the northeast waypoint. And we're setting the stack pointer to 3 or 5. Then we add that waypoint, then we do the same thing for stack pointer 7 or 9, which is southwest and northwest. Then that finishes that area. Then we're moving the waypoint stack pointer, which is the end of our path that we built up here. And we're setting that. So then we do we path to the home waypoint with the set waypoint to command, which is here. So we would travel the waypoint path from the mining area, which just peaks these 2 values. Peaks and subtracts, then peaks other one. And then jump to set waypoint, sets the target X and Y, and then it returns. Alright, so after the waypoint, the target X and Y are set, then we move to that target, read the data, and if mode is not 0, we jump back to the read data, and this has a wait command built into it, so it does the waiting for us. Then if it passes that, if mode equals 0, it goes to the next line and does another check. So if the stack pointer is greater than 100, which is where we started building our waypoint. So basically, if we're at the end of the waypoint or not. If we're not at the end of the waypoint, we jump all the way back up to here. So 1, 2, 3, 4. And set the next waypoint. And then do it all over again until we reach the end of our path. Then we reload the stack pointer from our saved stack pointer that we saved way up here when we started this little function area. And we reload the RA that we did up here, and we return back up to where we called this to here. So at this point, after we finish this, we're sitting at the waypoint that's outside of our base. We're sitting at this waypoint right here. So then we move to this waypoint that's inside of the hangar. Does that, it waits to finish, and then it loads its RA and returns from move shelter, which is called up here. So then we unload, we wait for that to finish, and we wait to charge. And if we're not charged, we keep waiting. Then we move the stack pointer to 100, and we do the set waypoint from, which is similar to a set waypoint to, except for in this case, we are going from 100 to the end of the stack pointer instead of from the stack, or from our waypoint stack pointer to 100. You're going 100 to our waypoint stack pointer. So we're adding instead of subtracting, and we're doing X first instead of Z first. Where's that? Up here. Then we're doing the move the target, reading the data. If the mode is 0, this is basically the exact same thing that we did down there, except that we're comparing it to our waypoint stack pointer thing. Then to let the other chip know that we're done, once we've reached back to where we started from, or at least the closest waypoint to where we started from, we set the target X and target Z to 0. That is to tell the other guy that we're done. That's the condition that it's waiting for. And that is the whole job of this chip. So let's move on to the chip that's below the LEDs. Okay, so this chip has the bot from the transmitter, that's basically the transmitter. Then we have the LEDs and the memories. This chip is responsible for handling the actual mining part and for telling the other guy, the chip that's inside the bot, the chip that we just looked at, is for telling it that it's full and it should take over and send this guy back home. So for that, we have the AIMEE hash. In the last version of this script, we had the AIMEE on a screw, but since we're out of screws, we're using a hash for now. And we're also using the minimum charge. We still have this in the other chip, but it's not used. And we have these 4 vertices. You'll note that they're in a different order because this is, optimized for not colliding with the boundary box instead of optimized for finding out which waypoint we need to drive through. Then we have the initialize. We're setting the mode of the charge thing, so it's a %, and we're changing the color. Turning the bot on and reading the data. And then let's see, initialize is here. Okay, so the read the data is down here. We'll come back to that because there's a lot of stuff into that one. Then if the mode is 0, we go to initialize. This is kind of how we did it the last time. And we have a safety check here. If the memories of X and Z are 0, then it aborts the thing and goes back to this. This is basically the startup area. When this is requesting a new mining location, it sets these 2 values to 0, and they don't get set until after the chip that is assigning the mining coordinates is done with it. So this is just an extra safety check so that when we're starting up the system, we don't have to do some fiddly stuff with it. And that's the only time this code should run is when we're first starting things off. But that passes that check, then we're setting the target X, Y, and Z. And we're setting the bot mode to move to target. We're not using path to target because we tried that last time and it did not work. Once we've reached the target coordinates, we then roam. And roaming just keeps roaming. You'll note we just fall through here, where there's no return statement here. So roam just keeps roaming until read data does something. Until read data intercepts it, or the mode does not equal mode roam. Back up here, we have a check here for the mode roaming. It goes back to roaming. And then the two things that we had in the last script. But the full function is rather different from this one, or in this one from the last one. We'll look at that in a moment. Actually, let's go ahead and look at that now. So full just turns on the AIMEE. It sets the setting, debug stuff to set the setting, and it reads the position X and Z. If those are both 0, like we said in the last thing, when the bot is gone unload and then goes back to where it was binding, then it sets things to 0. Until then, it is not 0. So it waits until both these are 0 before it turns the AIMEE off and then returns. And so read data is the other thing, I think. Yes. So read data is another thing. This handles kind of overriding the path to target thing to switch that to move to target, because the roaming thing uses path to target, so we have to override that so that it doesn't do the little flying up in the air thing. And we're also using the position that we're reading up here, the position Y for our target Y. We're updating that, as I mentioned last time we did the AIMEE script. That is something to keep us from having to see the Y coordinates and read the Y coordinates, because we do not know what they are going to be when we're using a kind of programmable mining coordinates like we're doing now. We're reading the charge of the charge ratio of the battery, and we're reading the minables. We're writing those, and this is something like we did last time. If the return address is greater or equal to read data, so if it's called below this, then it returns here. This is just so that we don't accidentally trigger the unload code when it's already unloading. So then if the charge is greater than the minimum charge, it skips this part. And this is how we tell the other script that we need to go charge. We just do that by setting the mode equal to storage full. Moving the RA command to R select, which is up here, and then jumping to full, because this returns to RA. So we have to save RA to where we want it to return. This is also how we would do weather events. If we had a weather sensor, we would compare that and AND it with this value here, and then do a check. So we would do a check here, and then another check, and then AND those two together and have them call this little section of code. Then, if our minables is 0, it goes to the request mining coordinates, which we'll check in a moment. But first, let's look at this whole part here, which is the boundary check. So it checks the position Z And it's going to the end of this list. It is peeking, checking if it's less than, subtracting 1, peeking, checking if it's greater than, and if either of those are true, it will return. And so it's checking if it's less than -25 or greater than 27. Z, it's outside of our base and we don't need to worry about it. Then it subtracts 1. There's a return check here. So if this equals 0 without it having returned, then we're inside of the base and we need to overwrite its little thing and go back to initialize, which will send us back to our mining coordinates. Otherwise, it loads our position X into the position to check and does the same check that it did with Z. It does that with X by using this command. And that is our anti-collision with the base check right here. So then for the request mining coordinates, so we do a jump AL to full, which should, let's see, where is this? Right here. So what we should do first is set the storage to full. Then do a jump to full. And that will tell it that we're done mining in the area and we want to go charge. We want to go charge to make sure that while we're moving to our new mining coordinates, we don't run out of battery and things don't happen that would break our other scripts. So that's what we're going to do there. Then we set our debug message here. And we load the position of X and Z. They're supposed to be somewhere here. What we should do first is set the position of X and Z. And this is to let the other chip know that we're done with our current mining coordinates and we need to do some stuff. But that needs to happen after this. So after that happens, then this are set to 0, which hands this control off to the other chip, the chip that we haven't looked at yet. Then we're reading until X and Z get set to a non-zero. And when that happens, this waits if they're still 0. So we add them together. If they're both 0, that R0 will be 0. And if either one of them are non-zero, then R0 would not be 0. This does mean that we cannot have a 0, 0 for our mining coordinates or it would break the script. But that's usually not a problem because 0, 0 is usually near where you settle and going to end up inside of your base collision box. So if those are both 0, we go to -4. So 1, 2, 3, 4 and loops. And it does that until they're non-zero, and then it just returns to the start of the program once that triggers is done. But that's that whole script there. And you'll note that this script here does not have anything that depends on which bot it is. It's only the first script that we looked at that has coordinates that are specific to which hanger the bot is going to go in. So we can use this on every single script or every single bot without having to change anything special for it. No need to edit it. It is universal. And now for the final chip before we can test this stuff. Well, the second to final chip. There's still one more thing I want to do. This chip is the math heavy one, and it took forever. It was difficult. We have the memory of theta, which, as I said earlier, we want to memorize and keep a record of our theta so that if we have to take out the chip and replace it, we don't lose our place in our spiral. So this is just the theta that the spiral is using, and we're saving it to keep a record of our spiral. Then D1 through D4 are logic transmitters. We could use the index command, as I said a bit earlier, but we're using the screws for this one, and I'm not aliasing the screws because I ran out of lines and had to delete the aliases. They're not, the aliases are not used directly. We're using indirect references, which we will see in a little bit. So we have all of our things, and there's one thing that I don't know if people know about. I don't see people using it very often, but you can do some there. You can have an alias that has two names, or you can have a register that has two names, if you want to do that. I don't generally recommend it, but if you're having like complicated math like this, where you have a lot of variables and there's just not that many registers, you can do that to help save some stuff. I'm not using that in here because this is confusing enough as it is. We have some constants here. We have the 2 degrees constants, which, multiply radians by this number to get degrees, multiply degrees by this number to get radians. We have the hash for the memory. We have B, which is the, B is from this number right here. Wander around looking for ores in a 15 coordinate radius. And now we have the base, center, X, and Z. This is just those four vertexes from the last 2 scripts. We took those and we find the center point between those 4. We also find the base radius from those points, just finding the distance between here and those points, which is the same because they're, equal and not equal. It's rectangle, not a parallelogram or something like that. Then we have the path arc. So the other script that we just looked at, the previous chip, once it hands off control of this chip, it's going to be somewhere on the circle, somewhere on the spiral, and we don't know where the next point on the spiral is going to be, and we don't want it to drive through our base, because at this point, the collision code is disabled, as the collision is waiting for the memories to update. So there's no anti-collision code. So we're using this chip here to move the AIMEE around the spiral to the next point. And we do that by moving it this many degrees in chunks of this many degrees from where it is until it's where it needs to be. Then we have 1 plus 1b, which is 1 plus 1 over b. And I did calculate this before, but I ran out of lines, so now it's constant. Okay, so those are the constants and the settings and all that stuff. So this is the stuff you need to enter for your own base. Everything else should be fine. We're sleeping for B, so B here is doing double duty, as well as the distance between spiral is also how long we wait between checks. Then we're addressing the memories, the various different color memory chips. We're addressing with the load index command, so we have the index starting at 0 here, and the bots we're addressing with where is it? Indirect referencing. indirect referencing or whatever this is called. I don't know what it's called. We're addressing this way. So those start at screw 1 through 114. So it starts at 1. Then we are loading X and Z. And we're ending those together. If they equal 0, we go to the next data. If they don't equal 0, we go to the next spot. And we keep looping. -7, which should be right here. 1, 2, 3, 4, 5, 6, 7. We keep looping until we've checked all the memories. So until the bot index is greater than 4, that will keep looping. Now, as I said before, we can use a theoretically infinite number of AIMEEs if we use the load index command for the bots. But we're not doing that. Then this jumps to main, and this is a whole little loop. This is the main loop. This does all the stuff, and everything else happens down through here. So next data is right here. We're loading the memory setting into our theta. If theta is 0, this is just startup code. These next few lines here, this part here is all startup code. We could not do that, just make you manually type in some kind of startup number, but I don't like doing that because people will screw it up. They won't enter the number, then they'll complain that it doesn't work, but it works. They just didn't do it right. But I added this code to make sure for this one little time when you run it, and the memory is 0, this sets the memory to 1, which is 1 times 1 degree times 2 radians. So it's 1 in radians. 1 degree in radians is theta, and the radius is base radius. So that's kind of the minimum of our spiral. It really should be base radius plus b, I think, but we'll see. Then we path to the mining location, which we will look at in a bit. So in every other time we run it where theta is not 0, or where the memory theta is not 0, in basically every other time it runs, we have all of this big giant thing. A quick refresher on the formulas that we're going to be using for this next section. R of theta is A, which is base radius, times B, which we've defined as the coordinates between the mining roaming location, times theta. Distance between 2 points, where distance is equal to B, simplifies to this equation. And then we want this to be between 1 and 1 plus b. So that is how we're checking between different thetas. Yeah, that's right. Then we added the thing a plus b and stuff over there. I calculated that elsewhere, I think. Then to convert from let's see, polar coordinates to Cartesian coordinates is x is r cosine of theta, y in this case z is r cosine or r sine of theta, and to go from Cartesian to polar, r is x squared, or the square root of x squared plus y squared, and theta is the arctangent of a z over x. And there's some caveats with this, which we'll talk about in a moment. Okay, so for this part, we are doing base radius, so r equals a plus b times theta, which, we calculate that, which is, these two numbers. And we're ignoring the offset since this is not at base center, but at 0, 0. We don't care about that for calculating the next theta yet. We'll care about that in the next thing. Then we save the two values we calculated. We add, or we use our increment we set that to 1 degree. As we go around and around the spiral, the distance between thetas gets really, really small. At the starting point, it's like 50 something degrees. Then by the time we get to 10 rotations, it's less than a degree. So we need to have a way to calculate that for a bunch of different cases. And that is what we're doing here. So we calculate the distance between thetas, which is doing that distance formula. So cosine of theta 2 minus theta 1 are 2 times theta 1 times theta 2 times cosine of theta 2 minus theta 1. And then it's theta 1 squared plus theta 2 squared. So theta 1 squared plus theta 2 squared minus 2 times theta 1 times theta 2 times cosine of theta 2 minus theta 1. And that number is saved in R0, which is what this does. And then we're looking here, and if this is greater than or equal to 1, it branches relative. If it is not, or if it's less than 1, then we add the increment to theta, and we jump back to here. Then, since we want to know if it's between 1 and 1 plus 1 over b, we check here. If R0 is both greater than 1 and less than or equal to 1 plus 1 bth, it will jump to path to new mining location, which is the same jump that we did up here. Otherwise, we divide our increment by 2 and say that in R1. Then we subtract our increment we subtract R1 from our increment, just in case our increment is, I don't know, a different weird number. And then we subtract our increment from theta. Then we jump back to JL, distance between thetas. So 1, 2, 3, 4, 5, 6, 7, 8. And that's a whole loop. So this is the exit condition of this whole loop. The only exit condition of this whole loop. Alright, so the next area, this is so complicated. We have path to new mining location. We have yield information, and we have a safety check here. We're checking the target X and target Z to make sure they're both 0. This lets us know that the full command is finished. The AIMEE has gone, it's charged, it's gone back to where it started, and it is waiting for further commands. Because if you remember, right before we set the memories to 0, we ran the full command, which called the first ship, which did the pathfinding. So if these are not 0, it loops and just keeps looping. Then we convert the theta from radians to degrees, and we save it in the memory. Technically, we could keep it as radians, but when I'm looking at the memory and trying to see what's going on, trying to debug things, I do not think in radians, I think in degrees, and I need it in degrees to figure out what's going on. You can remove that if you want to, but I think this is more user-friendly. If you can call this at all user-friendly, I'm not sure you can. But anyway, we're saving the theta and the radius that we calculated way back in this little guy up here. And then, oh god, this is so difficult. So the first thing we have to do is, all right, how to explain this? We are going to move our aimbot from where it is now to where it needs to be on a circle. So what we're going to do is we're going to take the theta, which is going to be some number of rotations, and we're going to mod that by 360 degrees. So we want to find the angle, we're going to divide it by 360 degrees and give us the remainder. That is what the mod command does. So we're just, doing that. And right here, we are converting our path arc from degrees to radians and saving that in increments, which, as we saw up above, is 5 degrees by default. Once that gets bigger, we may not want to use 5 degrees. We may want to change it. I don't know. I may want to do some kind of calculation with that. I have no idea. I may want to multiply our increment times path arc. That could be something we could do, which would work actually quite well. So I'll think about that. And then we read the bot position, which just reads the bot position in mode. Then we offset that to, basically we're offsetting that by the base center so that our thetas are in our thetas and radius, our polar coordinates are at 0, 0, so we're moving the bot coordinates to offset from 0, 0. Then we're converting that from polar, or converting that to polar. And this is complicated. This is so complicated. So polar coordinates, as we looked at, it is, the first part of it is theta equals arctangent of z over x. However, if one of those numbers are negative, it does not give you the right number. So then we have to worry about quadrants. And I don't know how much you remember about your math stuff in high school, but positive x and positive y is the quadrant 1. Then there's quadrant 2 at negative y and positive x. Then when they're both negative, that's quadrant 3. And when only y is negative, that is quadrant 4. So 1, 2, 3, 4 with the x-axis in the middle. Then, so if x is negative or greater than or equal to 0, we skip this line here. But if it's negative, we have a quadrant 2 or 3. And that means we need to add 180 degrees or pi to theta. And then we skip the next part if that is the case. So if it's in quadrant 4, which means that z is negative, and it's not this, then we add 2 pi to the theta, which is, 360 degrees. Some cases when we have like a negative z, when one of these are negative, theta would be negative. So this does not necessarily mean this is going to be greater than 360 degrees, but it might be. Then the radius part is, however, this. No need to do anything special there. And while we're up here, the Cartesian coordinates are thankfully fairly simple. We're just converting to Cartesian and we're adding the offset from the base. Because I'm calling this multiple times. And it saves lines. This stuff here is just to save lines. So we were right here. So what we've done is we've offset the bot coordinates to be based from 0, 0. Then we've converted those to polar, and then we're checking the theta of the modded polar coordinates from where we want to go to where we are at now. And if the bot theta is greater than the moving to theta, then we skip this line. So basically, if our theta is greater than old theta, then we subtract. So if this is basically, in some cases, we will have theta is greater than 360. That's what they were checking here, basically. Or we get weird numbers because the way I'm doing the next part is we're only adding to the bot coordinates. We're only going counterclockwise, I think. We're only going counterclockwise, and I'm not trying to pick which direction we need to go along the circle because that would take too many lines of code. So I'm just doing it this way, and it seems to work okay, sort of. Now we are moving So we've got our bot position in terms of polar coordinates, but we're going to use the radius from way up where we calculated the new theta. So we're moving the bot along the circumference of our circle, but we're doing it at a new radius. That is the radius that are the next ring in the spiral that it needs to be to, which may be either the same radius that it's at now, or maybe the next ring, or depending on how many rotations have been around the spiral between now and the last time it asks for mining coordinates. So we do that. We convert this to, then we add increment to theta, and we convert that to Cartesian coordinates. Then we set the target X and Z. So basically, we've rotated the AIMEE 5 degrees along the circumference of the circle of radius of old radius, which is the radius of the mining location. So we've done that, then we move the target, or we read the position. If the position is not 0, we keep looping and reading the position until it is 0. Then we check to see if our theta is less than old theta. If it's less than, then we loop back and we do everything again. So 1, 2, 3, 4, 5, 6, 7. We loop back to here. And we add our theta stuff, and we keep looping and doing that. We keep adding the path arc to our theta until our theta is greater than the theta that we want to go to. So we're just moving along the circumference of the circle until we reach the position, the theta that we want to reach. So once we've done that, then we're reloading the theta and the old theta from way up here where we calculated the theta. The theta for our mining location, and not the theta for the bot findings. Then we're converting that theta to Cartesian coordinates, or we're converting those polar coordinates to Cartesian coordinates. We are resetting the index for our memory, and we're writing the positions X and position Z. And then we're jumping back to main. It all is so complicated. Okay, let me look with some visual guides. Maybe that'll explain a little bit better. Okay, so if our bot is like here, it's been mining. It's been mining for a while. Other bots have requested things, and now let's say our theta is like right here. So what happens is the bot that's over here gets its coordinates converted to polar coordinates, so it finds out where it is on this little graph here. Then it gets its radius jumped up to the next line, to where, so mining, this is our new mining coordinate, so it gets its radius jumped up to here, and then it gets bumped up along the thing until it reaches that radius, or within 5 degrees of that radius. And then that number over here gets converted to Cartesian coordinates and saved in the memory, and the bot passes control over to the other chip, the previous chip, the one that handles the actual mining. Okay, so there's one more little tiny thing we need to do before we actually test this code. Now, you may or may not remember, like, way, 6 days ago for me, when we started this episode, when I was talking about this chip here, I mentioned some extra features I was going to add onto it, but because, hey, this is going to be super easy. There's not going to be anything about polar coordinates and all this quadrant crap. None of that is going to happen. I thought it was going to be easy. It'll take like a couple hours. I'll be fine. But no, that did not happen. I figured I was going to have extra code to add things onto it, but of course that didn't happen. I had to cut out lines and things. So, the thing we were going to add is a warning if the AIMEEs fall in a hole. And having tested this, I know that this is actually necessary, because AIMEEs are dumb as rocks, and they need help to keep them from doing stupid things. So what we're going to do is we're going to add an X, Y, and Z coordinate there, and we're going to add a mode here. We're going to add a flashing light as well. I guess we'll do it there, and we'll also add a siren over here. Okay, that's why it looked funny, because it was facing the wrong way. Can we not face those the right way? There we go. Okay. Volume, whatever. We can't hear it. We're in a vacuum, so that won't come into play until later. So what we're going to do here is we're going to batch read the AIMEEs. Oh, I did check, and we can use index and batch read on the transmitters. You just have to use the hash code for the transmitters and not the hash code for what they're pointing at. And we can use the index command to read those as well. We are going to use the index command to read these. We're not going to use the index command to read these. We'll use the screws for 1, 2, 3, and 4. And then for these two guys, we're going to use the hashes, the bash commands for them as well. And then let's just type all that out. It shouldn't take long, and this is one that might actually not take long. Okay, super quickly, let's look at this. We have the LEDs for X, Y, and Z, as well as which byte it is. Then we have the hashes for the transmitter, the flashing light, and the speaker, and we've defined a setting for the minimum Y before we start to worry about things. We sleep for 5 seconds, we load the Y position from the transmitter, the minimum Y position. If that is less than the minimum YX, we set this to 1 and return on this stuff. And if this is not 0, we go to update LEDs. If it is, it keeps looping. Then on update LEDs, we set this to -1. We count the number of transmitters, so this works for any number of transmitters. Then we add 1 to the index, which is why we started at -1. Then if index is greater than or equal to count, we return. Otherwise, we go down here, we load the Y position. That should be load index. As should this and this. So we load the index from the transmitter. We load the Y position. If that is greater than a minimum Y, we loop back up to the yield statement. And we keep looping until either we've gone through all the transmitters or we've found the guy that's less than minimum Y. And once that happens, we load the X and Z coordinates, and then we add 1 to index because index is 0 base and our AIMEEs are not. Then we write those values to the LEDs, and we return to main. Simple enough. There, so that should do that. Now we can actually finally test this. So our AIMEEs are waiting right here, are ready and ready to go with their batteries fully charged, and the Omni transmitters are on, keeping them fully charged. Now, the first coordinate is going to be 1, which should be out in that direction. It should be kind of lined up with the center of our base and out in that direction. So we have, this is the interior chip. As I mentioned, we are only temporarily doing it inside. The other AIMEEs all have their color-coded chip inside, and this just has a blank chip right here. Everybody else, they have the actual program. Okay, so this does not update, I don't think, when it's waiting for stuff to happen. It doesn't update. And where air tank is critical. Okay, so right, we just need to turn this on. So I've saved and everything should be ready to go. I think this is updated. I'm pretty sure I have the latest version of that script in there. Alright, so AIMEE is, oh yeah, we have to wait for B seconds. And we've waited for B seconds. AIMEE's going. So it's first it's going out to R. It's, you know, it's the same theta, but a different R. And it's kind of going far out there. It's like 40 something coordinates, I think. So that should happen. And now it's going in 5-degree little path segments. Which is going to take a while. Still going. It's now gone over, you know, it's this side of the base. It's in the north side. And now it has reached its mining coordinates. It is mining. Running back and forth and mining. I think the mining coordinates are, yeah, that's where the mining coordinates are. And then it's heading off to mine into the new area. It's roaming, I think, right now. So if we go back inside. A little bit harder to get back inside than it should be. You can see that it's now moving to target and stuff like that. It's roaming. The two coordinates have been updated. They're no longer 0. This guy is not updated. So if we go find the pink guy, he should be there. It's gone. They're not there anymore. They're off somewhere around here, somewhere over. Is that them? They're already way over here. So yeah, they've been pathfinding and just, you know, blowing by this guy because they don't need you anymore. We're going on to the next guy. So it should be B coordinates away from this guy's mining location, which hopefully is not in that crater right there. That would not be fun. And maybe that will trigger the alarm. Let's go check. I don't think we're going to make it in time. Can't sprint. Oh, it did trigger the alarm. So yeah, that's at -3, and it's not updating or something. Oh, -4 now. So that one's still waiting. Oh, we haven't actually turned it on. We'll wait for that to fix this stuff before we turn it on. So those guys are mining. That one's doing. That one's still. Hopefully, it hasn't gotten stuck. It's still down in that pit, it looks like. It looks like it might be climbing out now. It's a pretty big pit, so it shouldn't be too steep for it. But maybe it is. It is AIMEE number 2, so that's the right AIMEE. Let's go check on that guy. He may need a little bit of helping hand to get out of the hole. Are you AIMEE? Okay, that is not how you should be driving. I can see why you might be having some kind of trouble. You are not doing it right. I wonder if I can just carry it and it will figure it out. I probably need to know where it's trying to go though. And the pink one's coming back in to recharge. The purple or the blue one is trapped in a hole as well. And then the yellow one still has stuff to do. So this should come in and recharge. And the blue one has triggered the little safety sensor thing. So it's coming in, it should unload and charge. Okay, that's working. That is doing well. And I filled in that little hole a little bit, but apparently I need to fill in this little crater over here as well. And this is just, it's kind of, it's a lot of stuff. But yeah, this is taking so long, so we're going to end this episode here. It's going to probably take me at least a couple weeks to get this uploaded past the time the episode does or is goes live. If it's still not uploaded after then leave a comment, and I may have just forgotten because I've done that a few times. I log on to just specifically to upload scripts, and then I end up doing a whole bunch of other stuff and just completely forgetting about the scripts. So yeah, just remind me and I will get to that. Like if you like, subscribe if you're not. Thanks for watching, and I will see you next time.